I think it's about time to start. So, hello, welcome to the Think Tank. Our topic this year is data science, the sexiest field of the 21st century, at least as first claimed by Dilbert, for those of you who are fans of cartoons, but subsequently picked up by the Harvard Business Review, so presumably it's true. Actually, I've been looking at Twitter feeds, and if sexy is defined by what captures people's attention, and if that attention is reflected accurately in Twitter volume, the volume of tweets about big data is larger than the volume of tweets about our favorite HPC topic, exascale, by a factor of 100, at least 100. So I think it's, at least for the time being, sexy. So we have three panels this afternoon. First panel is about infrastructure for data science. The panelists are Sverre Yarp in the middle, who is the CTO at the CERN Open Lab. Simon Lin on the end, who is project director at the Academica Sinica Grid Computing Center. And next to me, John Schalf, who is CTO of the National Energy Research Supercomputing Center and the head of the Department for Computer Science and Data Sciences at Lawrence Berkeley Lab. So, I think infrastructure is an interesting aspect to data science. At this conference, we've had a lot of discussion about infrastructure and architectures for exascale computing. Some people feel exascale computing architectures are the appropriate ones for big data, data science as well. Others disagree. Certainly there are many other aspects to infrastructure to support data science, interconnect, bisection bandwidth, long-haul bandwidth, etc. But the experts are with us. So in general, the questions I have to the panel are, what is the current state of data science infrastructure in your region and around the globe, in your opinion, right? You're here as experts, not strictly representing your organizations, but for your own personal expertise, so feel free to express personal views. So what's the state of the infrastructure? In what ways does it need improvement? And how do you see it evolving over the next 3, 5, 10 years? And also don't feel limited in any way to these questions. If you wish to make other comments, please do so. This is supposed to be a very free-form discussion. So I'll start with you, John, perhaps next to me.
Okay.
Yeah.
Hi. So I did bring. I went through the archive and found a bunch of old, things. So this is Brain Science and Data Intensive Computing is the Future of Supercomputing from '99, and DOE has its Data Management Challenge from 2004. We have been in the big data business for many years, but I guess the key for architecting our infrastructure for the future is to know what the objective is as opposed to the object, because everybody comes out of the woodwork and says they have big data. The objective in DOE has been traditionally big experiments, light sources, kind of like the CERN, is one big data source. And so we architect for the objective, and not that the data is big. We can always buy more disks. One thing that we've seen recently in the data sciences is, in terms of infrastructure, is that the light sources used to have a lot of processing near the experiment. It's getting to the point now that you need to actually have a lot of back-end processing, and we might be shifting a lot of that to large data centers. And it isn't a question of infrastructure buying more infrastructure, it's more of a question of getting that workflow to bring that stuff to the right location to do the processing. The other part that's kind of missing is statistics, and statistical summarization is getting to be a big deal, and yet statistical algorithms aren't designed to scale or be parallel now. And that's probably the 10 giants, I think, of big data are really about statistical algorithms and scaling those. With regard to the exascale and big data, I don't think we're going to do big data on tiny machines. And I think that the challenges that we're talking about in exascale are also challenges for big data when it comes to architecture and infrastructure.
Thank you. Sverre?
Okay. So I think I'm happy to say that we feel that we're in the right place at the right time. So we've been able to build up the infrastructure around the Large Hadron Collider that has allowed us to make the discoveries and cope well with the enormous amounts of data we have with the current infrastructure. Yet we think there are many challenges ahead. Simon will probably talk more about the distributed side of the computing we do. So I'll try to talk a bit about exactly what goes on centrally. So one of the problems in seeking even better architectures for big data is exactly, for instance, things like power efficiency. So today, we've actually come to the limit of our computer center. We've had to go to remote computing center just to cope with the amount of not CPUs consuming power, but also all the storage elements, of course. And that continues to be a challenge. Then we would actually be interested in doing exactly the opposite of what John mentioned, which is to move more intelligence in the direction of the sensors, because today we're very scared of actually losing data forever at the source. And since two physics collisions are really strictly identical, you have to analyze each one of them, and they happen at a frequency of 40 megahertz. So the more intelligence we could actually push down in terms of flexible architecture also being available with fast interconnects, bigger memories, and more sophisticated CPUs, we think the better off. We'd still need a lot of offline capacity further down the stream, but we would optimize already at the sensor level.
Thank you. Simon?
Yeah, actually, we, in a sense, was, I think there seemed to be an argument saying that the big data is for the HPC only, because the internal bandwidth within a HPC system is actually easily, larger than the global bandwidth, for example. But the cases where these large hadron colliders that actually, it's actually one of the very few examples actually in the production of this big data science. I think it definitely qualifies as big data. It has all these sort of the V3 qualities, and with the actually 1 petabyte per second, but then all that chunks have been taken away, and then eventually it was 20 petabyte per year. So under the framework, for the current status in Asia now, I think we have about 38 sites in 16 countries. I was saying that it's not all energy physics though. So altogether we have about 20,000 cores, CPU cores, and around 14 petabytes, more than 14 petabytes. And I didn't know the total data in and out, but from my tier 1 site, we in last year, we have more than 9 petabytes of data in and out, because the data has to go from tier 0 into tier 1, and tier 1 has to go to tier 2, etc. So I think this already kind of been quantified as a real production example of how this big data has been carried out in these cases. So, and then actually it's not that much processing. I mean, in Asia we're doing about 3 million jobs per month. Their jobs are actually reasonable. It's not too small anyway. So, and then one actually takes advantage of that and being able to do something. If we have time to talk about that, it's actually extended to the areas where the sort of concerns more the people, like sort of data science for the people, including the, they also have to test on the drug discoveries, and usually they don't have that kind of facility in many of the countries. And then also the data center for the earthquake and tsunami. And so all these natural hazard things has already been started being coordinated. Yeah. So.
Thank you. To me, at least, it seems that data science is a very broad and inclusive idea. And certainly, there are elements within it that we've thought about fairly carefully. For example, analyzing and visualizing scientific data from simulations, from experiments, to a certain extent from observations like the Synoptic Sky Survey or the Coming Square Kilometer Array. There are other areas where it's at least not clear to me that we've taken as careful a look. I'm thinking mostly sort of unstructured data areas, data from social networks, data from the coming, or I guess it's really here, starting to be here, Internet of Things. Eventually with sensor development, the Internet of Us, where we'll be looking at a lot of data coming from distributed and very diffuse sources. It seems, on aggregate though, it may be a very large volume of data, and the rates may be very large. It seems that data will be much more dependent on good long-haul bandwidth if it's going to be analyzed at, aggregated and analyzed away from its point of origin. So, so in that whole set of issues, do you have any particular thoughts, or what are we? Is everything going to run very smoothly there, or where are the bottlenecks? Sverre?
So with the LHC computing grid, we actually have good experience of distributing the data all the way around the globe, and I'm actually very pleased to see. I mean, we're building a sister data center in Budapest, and we're going to have dual 100 gigabit links into that. So, we're all amazed by the flops we get every time we meet, twice as many. We actually, when we meet, get also high increases in data rates across even transatlantic links. One would hope that would continue to open up, because really optical fibers can handle enormous amounts of data. So, I think for people who are going to do, analysis of social networks, the opportunity is there. I think they just have to be very careful that, the data they start with is sound and coherent, and then further downstream, I think it's going to be okay. Since you mentioned that, let me also just briefly make some publicity for the conference we're going to have as a daughter conference of this one at the end of September, where our slogan is big data where enterprise and HPC meet, exactly to discuss and iron out these things.
Good. May I? Sorry.
Please, we're almost out of time, but I'd like to get some brief comments from each of you as well.
I would just add on, maybe we are here all overwhelmed by this sort of extreme case, but then in Asia, a lot of smaller scale, but with all the features, including one with the Sakaguchi and on the earth science. But then one of the projects we involved with was we started using the quake catcher, which is Stanford sensor, and we work with various communities. Now we have almost thousands of them. So they're going to spread it to quite a wide area. So like you said, but luckily this kind of sensor do not need that quite kind of bandwidth. But we do have the network problem in Asia, if we had time to discuss about it anyway. So it's something like in a sort of small scale way, well, compared to, the data rate is much lower. I mean, thousands, we eventually will be building tens of thousands of them. And in order to complement what this sort of more expensive sensor can do.
Thank you. John?
So I think we're just, when we look at what actually spawned the reinterest in big data is like the Googles and stuff like that, and certainly NSA and other three-letter agencies have been in this big data, unstructured data business for a while. They don't tell us too much about their methods, and there's even more secretive places like Google and Facebook that tell us even less. And so we've kind of evolved away from them, but more recently we've been seeing stuff like what we're expecting to get from the BRAIN initiative, where, as Sverre said, you need to embed more processing next to the sensor, certainly, to reduce the data before you get it out of the machine. But then the back-end reanalysis that we're going to need to understand the function and the structure of the brain is going to require analysis and reanalysis and reanalysis of the winnowed down data that's been accumulated in these back-end data centers. So I think there will be increased interest in the future in the unstructured data, but the development of the techniques and the tools in the open market, I think that's going to be an interesting social and not so much technical issue.
Thank you. This has been a very interesting discussion. Unfortunately, we're going to have to leave it here. I wish we could continue, but maybe another time. Thank you very much, panelists.